Okay, here we go, folks. A lot of stuff here. We're going to do 2 problems just like it. And I don't care what the directions say in your assignment today in the book. This is what you want to do. And we will find all rational zeros. Rational zeros are anything that can be expressed as a fraction. And irrational zeros are square root numbers. Okay? Square roots. Those are examples of real solutions, meaning you can find them on a number line. They are not complex solutions. We're going to talk about complex today, complex being imaginary parts of solutions. That's more of chapter 5, we'll get to it, but for today, everything will be real. Whenever appropriate, use the rational roots theorem. We will do that. That's something you want to list on your work. Upper and lower bounds theorem, you will not do that for your assignment. You will not do the upper lower bounds theorem. I will talk about that today, but you won't apply it. The extent of your learning for the upper and lower bounds theorem is the extent of what you learned yesterday in your assignment. As long as you do that, you're fine. We will do Descartes' rule of signs because it's awesome. We will use a quadratic formula. We will factor, and we will sketch a graph. So we're doing all that stuff. If you don't understand something today, you must stop me and ask a question. Your test is going to have like 4 problems just like this. This is what you need to be able to execute on the test. How many total real solutions could this polynomial have? 3. If it had 3 real solutions, how many complex solutions would it have? None. It can only have a total of 3. So if it has 3 real, there aren't any complex at all. I told you yesterday, if there are complex solutions, they come in pairs. So for example, one of these is real, one of them is complex. Which one's complex? 4 plus I. If 4 plus I is a solution, and 4 minus I might be a solution as well. Okay? So they always come in pairs. You always have more than one. Always. So, let's say you did have complex solutions. Could you have just one? You can only have even numbers. So you'd have 0 or 2. Question. You know a quadratic formula? So if you worked out the quadratic formula, you could get something like this. Say 8 plus or minus the square root of negative 4 divided by 2. Reasonable, right? What is the square root of negative 4? 2i. You can divide both those by 2. 4 plus or minus I. So you have solution of 4 plus I, and you have a solution of 4 minus I. So see how it works on a quadratic formula that you have plus or minus? Therefore, that imaginary part, you'll always have a positive and a negative part of it. That's why you'll always get 2. Always come in pairs. So if you solved a polynomial, you got 3 answers. Let's say we had one polynomial had negative 1 and 3 and 8. Okay, those are all real solutions. Let's suppose that you had imaginary. Let's say you had negative 1 and 4 plus I. You would also have 4 minus I. You cannot have, say, negative 3, 1, and then 4 minus I. That is not possible. Always has to be pairs. Always has to be 2 things with i's, or 4 things with i's, or 6 things with i's. Better? Question. Yeah. Yep. I only happens when we take even roots. Yep. that's a loaded question. There's a lot more to that, but we'll get to that second semester. Excellent. So if I had 3 real, I would have 0 complex. If I had 2 that were complex, how many real would you have? 1. Now let's think about that. I'm going to make a statement here. This polynomial has at least 1 real solution. True or false? True. True or false? If it has 1 real solution, it must cross the x-axis at some point. True, that's what it means to be a solution, cross the x-axis. Now let's think about why that is. If I draw a 3rd degree polynomial, okay, everybody agrees it looks like that, right? Something like that. If I draw a coordinate plane, an x and y axis, can you draw that shape and not cross the x-axis? I'm trying. I guess maybe I could stop right there. Look, smartboard, I made it blow up. It just died. You can see that you're going to cross it. I mean, you could try to slow down, but eventually you're going to cross that spot right there. We all know that. Okay, come back to life. Still red. Come on. Should I kick it? We should stop. Come on. Well, fortunately I know how to fix it. So. There we go. As you can see, you can say, oh, I don't want to cross it, don't want to cross it, don't want to cross it. Oh, I got to cross it. So, you got really no choice, okay? It's going to cross. An odd degree polynomial is going to cross at some point. There's no 2 ways around it. So as you can see, it shows up that you're for sure going to have 1 real solution, okay? All right, let's talk about the other part now. This is what we learned yesterday. Let's talk about those real solutions. Let's talk about the positive real, and let's talk about the negative real. The positive real solutions, we look at the polynomial p of x, and we look at the sign changes. Do I change signs there? Positive to negative. Do I change signs here? Here? So how many times did I change signs? Twice. So there are either 2 positive reals or 0 positive reals. We decrease by a factor of 2. If I want to look at the negative reals, what do I have to do? Yep, p of negative x. You got to punch in that negative x, and you get negative x to the 3rd minus 3x squared plus 13x plus 15. Exactly. When you plug in a negative x, the odd exponents will have the sign change. The evens will stay the same because if you square a negative, it just becomes positive, so that doesn't result in a sign change. So as you can see here, you now have a negative. This stays negative. You have a positive instead of a negative, and then the end one's positive. Do you have a sign change here? 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 So you have 1. Well, not necessarily. We for sure have 1 negative. If we have 1 negative, we could have 2 positive, and that would make 3. Or you could have 1 negative and 0 positive. That would mean you have 2 complex. So we'll see how the situation works itself out. So now let's work on actually finding the solutions. You don't know how to find the solutions unless you use the rational roots theorem. So let's list our choices for the rational roots theorem. Whoop. And you remember that the choices are going to be the factors of your last term divided by factors of your front coefficient. So, what are my p's? Very good. What are my q's? You take your p's and you divide them by your q's. So your choices are plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Those are my choices. What would you like to try? Let's try 1. We know that 1 is a reasonable choice. 1 is positive, and is it possible that it has positive solutions? It's possible it has positive solutions. So 1 is a realistic choice. Let's try it. You plug in 1, you get 1, minus 3, minus 13, plus 15, which is negative 2 minus 13 is negative 15, plus 15 is 0. 1 worked. If 1 works, what's a factor? X minus 1 is the factor. So let's take this polynomial, divide it by that factor in order to get a polynomial that's of a smaller degree. So I'm going to divide it using synthetic division. Question. Good question, because they're often the same. You always drop that number down, and then you multiply by the number in the box. Always drop down the first number, the first coefficient. So if it was a 2 here, you drop down a 2. Okay, I end up with an x squared. So the question was, did this thing factor? Well, it does. We didn't know how. We figured out how it factors. Factors this. Does x squared minus 2x minus 15 factor? Very good. X minus 1 times x minus 5 times x plus 3. So the last thing we will do before we graph it is list our roots or our solutions or our zeros, whatever you want to call them. What are they? This is my favorite part of the process. How many real solutions do we have? How many complex? So that's the scenario I came up with. I have 3 real and 0 complex. How many positive solutions do I have? How many negative? So I came up with that option. See, it makes sense with what we have. It's a good way to check your work. And now we can graph it. And graphing it is the easiest part of all. We just plot negative 3, positive 1, positive 5. And there we go. What I love about this is it takes everything we've ever learned in mathematics, as far as algebra is concerned, puts it all together. Question, Taylor. You raise a good question, but other people might have it as well. This graph, positive or negative? Positive, so it finishes going up. It's odd, so it starts down, finishes up. Okay, so starts down, finishes up. Single root, so it just passes right through those. Okay, got it? You're going to have 4 problems for your assignment, and they're going to look like that. Except, let's do one more. So that was a 3rd degree. Let's do a 5th degree. So there was a while where I wasn't teaching. I was just working at a camp. I shouldn't say just. It was a very big job. But I missed doing math so much. I brought a math book with me to work, and I would do math once a week. I just think this stuff's really exciting. All right, so we got real, complex. We have positive real. Caitlin, are you laughing at me? Are you coughing because you were trying to keep from laughing, and that was your way of disguising the voice? You saying, I can't believe he would do math at his job? It's okay. I'm used to being judged. I'll take it. Let's do it. How many possible real could you have? 5. How many complex would you have then? 0. If I did have complex, they come in pairs of 2, so I would have 0 or 2 or 4. So if I had 2 complex, how many real would I have? And if I had 4 complex, I would have, see the relationship there? Now let's look at our positive reals. That's the sign change here. Do I have a sign change here? Yep, positive to negative, so that's 1. Negative to negative, negative to positive, positive negative, negative positive. So I have 4 sign changes. So how many positive reals could you have? 4. Yep. Question. Yes, exactly. The complex solutions drive the number of positive reals. That's the whole less by a factor of 2 thing. And I wish that your book talked about that in this section, but it really doesn't. So I kind of introduce it as we go. So it doesn't give you a reason why we reduce it by a factor of 2. Negative reals, we have to do negative p of x, or p of negative x. Let's do that. And as Crystal said earlier, only the odd powers change value. Do you see why? Positive powers, you know, the negative just goes away. So if we plug in the negative, you're going to have negative x to the 5th minus 3x to the 4th plus x to the 3rd plus 11x squared plus 12x plus 4. How many sign changes? 1. It goes from negative to negative, so no sign change, then negative to positive, so that's 1 sign change, and then it stays positive the rest of the way. So you have 1 negative real. Well, doesn't that make sense? If you have 1 negative real and 4 positive, that makes a total of 5. If you had 1 negative real and 2 positive, that would make 3. 1 negative and 0 positive would make 1. Again, it's a 5th degree polynomial, an odd polynomial. So true or false, this thing has to cross through the x-axis. It has to. That's why you are for sure going to have 1 solution. Okay? Have to. Okay, let's list out your choices. What are your p's? 1, 2, and 4. How about your q's? And let's divide them. Plus or minus 1, plus or minus 2, and plus or minus 4. Can you factor that? I don't know how, so I need to use the rational roots theorem. What number would you like to start with? Good choice. Does 1 work? Let's see, 1 minus 3 is negative 2, minus 1 is negative 3, plus 11 is 8, minus 12 is negative 4, plus 4 is 0. 1 worked. So what's my factor? X minus 1. What do I do now? Synthetic division. 1, negative 3, negative 1, 11, negative 12, and 4. Somebody was doing work today and they didn't come up with a 0 for a remainder. They came up with 3. And you know, immediately they raised their hand and said, what's going on? Well, what they had done is instead of writing negative 3, they wrote a positive 3 in their problem. And so it's a good sign that if you don't come up with 0 for a remainder, you made a mistake somewhere. And you need to go back and find it. So we have x to the 4th minus 2x to the 3rd minus 3x squared plus 8x minus 4. Does that factor? Not that we know of. 1 worked the first time. Is it positive I could have more than 1 root? Yeah, it's positive I could have 4. So 1 could be a single root, it could be a double root, it could be a triple root, quadruple root. If it worked once, try it again. Let's try 1 again. 1 minus 2 minus 3 plus 8 positive 4 minus 4, 0. 1 works again. So I have another factor of x minus 1. Let's divide it. I need to go to a separate sheet of paper. Got it? That's what I get. Okay. Scott sees 1 does work again. But even before I use the rational roots theorem, whoop, I'm sorry. I was just trying to copy it from memory. I remembered the 4s, forgot this part. So when you have this, 1 does work. But at this point, I say I'm done using rational roots theorem. Does anybody see how it factors? Factors by a method of grouping. Very good. What can you take out of the front section? Second section? -4. What do both of those share in common? Does x squared minus 4 factor? So you've got 1, 2, -2. Exactly. 1 is a triple root. So did you get that? I can see you moving your head around. Some tall people in front of you. Okay, so we go over here, and so we said x minus 1 is, Grace just said, it works 3 times. And then you have x minus 2, and then you have x plus 2. So you've got all 5 of those, okay? And so your roots are 1, 1, 1. Or you could write 1 as a triple root, or you could write 1 as a multiplicity of 3. Any of those would be acceptable in my class. You can also write then 2 and -2. The last step is to graph it. So once before we graph it really quick, because this is my favorite part, how many real solutions do you have? And 0 complex. So that's the one we came out with. And how many are positive? 4. How many are negative? So you can see we found our 1 negative matches with the 4 positive. So it all matches together. Krista and then Grace. Complex would be if you came up with like imaginary. So let me show you an example really quick because it's a really good question. Let's suppose you were doing this problem and instead of an x squared plus 4, let's suppose you had instead of x squared minus 4, let's suppose you had x squared plus 4. Well, the solution here is 1. The solution here is, well, you take x squared plus 4 and set equal to 0. So x squared equals -4, square root, and you get x is equal to plus or minus 2i. So that'll be a situation where it's like, oh, well, we have 2 imaginary then. We have positive 2i and negative 2i. And so those are complex solutions. Complex and imaginary, really, for your terminology, is the same stuff. Okay? Grace, you had a question? You don't know it's going to be 4. Like I said, in this scenario, we came up with, well, if that was your case, you would have -1 as a solution, so that'll be your 1 negative. And then you would have, your 2 imaginary. So you don't know for sure. Or maybe I'm missing it. Let me look again, just make sure I see your question. No, you could have 1 negative and 2 positive, and then 2 complex. So this could be another option. So the green one could be one option. Another option could be the blue option. So that would be 2 complex, 2 positive, and 1 negative. That 2 positive, 1 negative is 3 real. Or you could have 1, 1, 4, 0, 1. You could have that as well. So you can have those different options. Good question. Okay, the last thing we need to do is graph this. Let's graph it. I'm going to get some extra space. If you don't have room, you can just watch mine. We've got 1 and 2, 1 and 2. And I've got negative 2 as a root, 1 is a triple root, and then positive 2 is a single root. This is a 5th degree polynomial. Is it positive or negative? Positive. So it finishes up, it starts down. Single root here, triple root there. So I'm going to go up. I'm going to do my little triple root action there, and then pass through right there. And that's what it looks like. Isn't that cool? We discovered that from, that type of work. We figure out the nature of the graph, what it looks like, and the type of solutions. Very interesting. So, what I want you guys to do is, for your assignment, I would like you to work out of your book, page 288, 67 or 65 through 67, then 69, and there's just 4 problems, just like what we did today in class. Okay, I want you to do the exact same thing we did in class. Whatever the directions say, do what we did. And I want you to know that right now, as you see here, we've listed off 4 assignments from this unit. I checked with what I've done in previous years, and in previous years by this point, I've had 3 additional assignments already. So what I did is I tried to get rid of the extra stuff. I said we don't need to quite do that many assignments, and we can, kind of skim over some of the material a little bit. I didn't give you guys an assignment on dividing polynomials, did I? No. And I didn't give you an extra graphing assignment. This is where we're at. So what means is, good, we have less work. The bad part is you have less practice. So you got to make sure that you do these problems. Don't leave a couple of them off. I don't just pick 4 because I'm like, well, that's all we need to do. I picked the 4 that are very useful for you to do. So you want to make sure you get each one, because that's going to be how you practice for the test. Right now, tomorrow we'll do section 3.4, which will just take us 1 day. You guys will fly through it. And then we just have 3.5. And 3.5 is almost identical to what we did today. Almost identical. So really, you're about almost at the end of your learning. You've covered just about everything you need to. So, question 1, question 2, and question 3 right after I press stop. Goodbye, YouTube Nation. Is there anybody missing from class today? There isn't. Wow. So I guess, Stephen, what's your mom's name? Ruth? Ruth, we hope you're doing well. Enjoy the video.